Welcome to our presentation on exploring the early universe with the Lunar Cryogenic Liquid Mirror Telescope prepared by Farah Afika, Siti Amina and Alia Maisara, myself, from University Technology Malaysia. The idea of using liquid mirrors for telescope has a fascinating history. In 1991, Ermanno introduced the concepts highlighting its potential for creating large, lightweight and cost-effective primary mirrors. Fast forward to 1994, the University of British Columbia constructed the first zenith pointing liquid mirror telescope, demonstrating the feasibility of this innovative technology. In 2004, Roger Engel proposed the concept of a lunar-based liquid mirror telescope which could observe the early universe by focusing on the zenith sky. By 2006, Alpaca project aimed to combine liquid mirror technology with conventional optics to provide a well-constructed 3-degree field of vision. And in 2008, a study suggested that a 20 to 100 meter liquid mirror telescope on the moon could detect objects 100 times fainter than those observable by James Webb Space Telescope, significantly advancing our understanding on the early universe. The proposal to construct a large telescope emphasizing its unique liquid mirror characteristic has been made, and the lunar environment is particularly well suited for the innovation as it allows for the creation of large, high-quality parabolic primary mirrors through the process of fluid spinning. However, there are several limitations to consider. First, atmospheric and thermal interference makes ground-based telescope ineffective in the infrared band. Second, telescopes like the James Webb Telescope have limited capabilities to monitor highly redshifted faint objects. Third, the high cost and the need for multiple launches pose significant challenges. Larger free space cryogenic telescope would require substantial construction and operational costs. Lastly, building and maintaining such a massive telescope on the moon would necessitate dedicated infrastructure at the lunar pole. The primary objective of this study is to assess the viability and scientific significance of constructing zenith observing liquid mirror telescope on the moon. With diameters ranging from 20 to 100 meters, this exploration aims to determine if such a telescope can provide the unprecedented insight.
Okay, so next we move on to the next part of this experiment, which is the theory of this experiment. So, what is the theory talk about? So, first theory discuss about managing thermal noise in infrared telescopes in the moon. So, the telescopes that observe in the infrared spectrum, such as the liquid mirror telescopes on the moon, must contend with thermal noise. So, this thermal noise is essentially unwanted radiation that is created from the telescope itself if it is not cold enough. So this noise actually can interfere with the detection of faint astronomical signals. And then, infrared light is particularly sensitive to heat. If the telescope components are not kept at very low temperatures, they will emit infrared radiation. And the second theory discuss about the cryogenic temperature control for liquid mirror telescopes. So the liquid mirror telescope use cryogens to precisely control the temperature and the stability of their liquid metal mirrors. This is important for keeping the mirror shape and reflective properties because the mirror shape and reflectivity can change with temperature fluctuations. And by keeping the mirror at a consistent temperature, cryogen also help to keep the mirror at a consistent temperature, making sure it gives optical performance on the telescope. So the third theory discuss about how the role of cryogen in minimizing thermal noise for enhanced detection. So, every object emits radiation based on its temperature, known as blackbody radiation. So, by cooling the telescope at extremely low temperatures, the emission of this unwanted radiation is minimized, allowing the telescope to detect faint and distant objects with greater clarity. Thus, the role of cryogen gives efficient cooling. So, cryogens such as liquid nitrogen or helium can cool the telescope components to temperature close to absolute zero. This drastic reduction in temperature effectively diminishes the thermal noise. And the last theory discussed about enhancing telescope sensitivity and image quality with cryogenic technology. So the cryogens also enhance the telescope performance by reducing thermal noise. With lower thermal noise, the telescope becomes much more sensitive and allowing for longer observation periods and enable them the detection of objects that would otherwise be too faint to see. The precise control over temperature and stability provided by cryogens is important for achieving high-quality image and maintaining performance of these telescopes. So next, the illustration shows the 8-meter liquid mirror telescopes in Chile was planned to build.
Next is about the experimental method. The first one is the stability of rotating mirror. A good pairing needs to hold up the spinning liquid mirror firmly without bending or flexing too much so that they keeps its shape and doesn't shake or change shape when the liquid mirror spins in space. This is because if the mirror wobbles or changes shape, it can't focus light correctly and the telescope won't work well. The second one is about reflective coating. The experiment successfully demonstrated that the ionic liquid could be coated to achieve the necessary high reflectivity surface. Why they use ionic liquids? It was explored and tested if they could be used to cover a liquid mirror in a telescope on the moon. These liquids were chosen because they have the properties like low vapor pressure. That means they don't turn into gas easily and can stay as a liquid even when it's super cold. This makes these ionic liquids a good choice for working in space where it's very cold and there's no air. This figure shows a 2-inch diameter flat liquid mirror. It is made up of an ionic liquid with a thin layer of silver coating on it. They applied a 3 millimeter thick coating of ionic liquid. Across the outer layer of these small layers, a thin transparent skin forms. They then coated this liquid skin with silver to create a highly reflective silver surface. The thin skin likely prevents the silver from diffusing into the liquid during coating. The second figure shows a standard reflectivity curve obtained from the experiment. From this graph, we can see that the silver layer achieved a reflectivity of 92%, although it had a few visible wrinkles that are visible with the naked eye. Going to the application, the first one is studying the early universe. For example, a lunar liquid mirror telescope LLMT is a type of telescope that uses a spinning liquid like mercury to create a reflective parabolic surface which acts as a mirror to collect and focus light. The LLMT can measure metal absorption lines, which are specific wavelengths of light absorbed by metals in the intergalactic medium using light from very distant galaxies at a redshift of Z equals to 10. A redshift of Z equals to 10 indicates a very distant object whose light has been traveling for billions of years. This allows astronomers to explore the early history of the universe. Next application is it can improve observations. The figure shows the examples of a liquid mirror telescope. The liquid mirror telescope could detect objects 100 times fainter than the James Webb Space Telescope JWST, meaning that it being able to see things in space that are extremely dim or difficult to see with the naked eye. So, it can provide more detailed images and spectroscopy studies of distant celestial objects. The last application is infrared astronomy. In this statement, the telescope mainly uses infrared light. Infrared light is a type of light that is invisible to the human eye but can be detected by special instruments like infrared telescopes that can penetrate dust clouds, which is invisible to our eyes but can be detected by special tools and observe the regions of space that block with visible light. By doing this, it gets a better view of how stars form and other things happening in space.
So in conclusion, the cryogens play an important role in the operation of liquid mirror telescopes on the moon by reducing thermal noise and preserving the liquid state of the reflective mirror. And the second one, the technology allows this telescope to perform optimally and providing exceptional opportunities for astronomical research and enable the scientists to explore the universe with remarkable clarity and more depth. And lastly, utilizing cryogens helps us to overcome the significant challenge of the lunar environment, thereby enhancing our understanding of the cosmos. That is all from us. Thank you.